All right, people, not one law of thermodynamics, but two laws of thermodynamics in this module. So we're going to get into this third law of thermodynamics and this whole business on third law entropies. So two laws of thermodynamics for the price of one module. Okay, so stated plainly, third law of thermodynamics says the entropy of a perfect crystal at 0 Kelvin is 0. And so if we want to think about this in context of like this quantity, our standard molar entropy at 0 Kelvin equals 0. Okay. However, this kind of seems at odds with the second law of thermodynamics, which states it is impossible to cool an object to 0 Kelvin in a finite number of steps. That's one of many ways we can state the second law. And recall, this is related to that thermodynamic efficiency equation, which says temperature of some cold object is 1 minus thermodynamic efficiency times the temperature of that hot object. And remember, this states that we can never get to 0 Kelvin because we can never have a thermodynamic efficiency of 1 or 100%, right? We can get very close to that. And in this whole business of, finite number of steps, right? So like in each one of these steps, we could pump heat out of an object, although never at 100% efficiency. So we can cool it down a little bit, and then we can cool it down a little bit more, and then we can cool it down a little bit more, but we can never quite get to 0. So another way of stating this is given by the Nernst heat theorem. So that's the same Nernst from the equilibrium expression. Nernst heat theorem. And I'll just kind of write this one out plainly. This says the change in entropy will tend down to 0 as the temperature tends down to 0. And that's a more realistic way of looking at this, that we can get very, very close to 0 Kelvin. And as we do, our entropy will get very, very close to 0. So now I showed you these graphs in the last module, this idea of entropy decreasing as we approach 0 Kelvin. So on the scale, right, that's temperature down here on the x-axis. And this is the origin, 0 Kelvin, 0 entropy, right? And so now the idea behind this and what's going on with this Debye approximation is we attempt to measure the heat capacity. Remember, that's what the measured quantity is. We measure heat capacity and determine entropy through that measured quantity. So we can measure it down as low as we can get. So let's say we're measuring, each one of these represents a data point, and then those get converted into entropy via that relationship. So we get down as far as we can go, and let's say that that's as far as we can get. Okay. So the Debye approximation says, well, we will approximate the heat capacity, CPM, as a function of T. So let me make sure that that's proper. CPM as a function of T equals some fit constant times T raised to the third power. So that is our Debye approximation. And that approximation kicks in once we're kind of at this point where we can no longer measure changes getting down to 0 Kelvin. Right? So then if you think about those integrals that we put together, right, where we integrate from 0 to the melting temperature, from the melting temperature to the boiling temperature. So in effect, what we would really do is measure, we would integrate from 0 down to some temperature, and I'll just mark that temperature T right here, where now that's going to be related to AT to the third power. And remember, CP divided by T, dt, so obviously that will become AT squared dt. But then we would integrate the expression from this T up to the proper melting temperature, where now my CPM is the known CPM of the solid state, which again, that CPM of the solid state might have its own equation with its own fit parameters. However, because we can't really ever truly take that down to 0 Kelvin, we could split those two integrals up into those two sections. The Debye approximation, the Debye approximation section, and then the section of the solid for which we have heat capacity data. Okay. So after doing that, that gives us what we call our standard third law entropies. So let's highlight that. And the symbol for that is given right there. So I drew that on that previous slide, right? SM with that little, sometimes I just put a 0, sometimes there's like a little crosshatch there. And so what that signifies is the molar entropy from, in this case, right, the standard means 298, all the way down to 0 Kelvin, okay? So now when we get that quantity, when we get our proper standard third law entropies, this is what finally allows us to calculate microstates. And recall that relationship goes as follows. Molar entropy equals K Boltzmann ln W, where now that is my number of microstates. And in our live lecture, we'll play with some of these values in reverse engineering this calculation, so we can take the molar entropy value and determine the number of microstates. But what I want to point out here is it tracks like what we might expect. So we can see graphite and diamond have very small standard third law molar entropies, meaning they will have a small number of microstates. But if we look at something like sucrose that has a much larger standard third law entropy, or just molar entropy, that means it is going to have an enormous number of microstates in comparison to just regular old graphite or diamond. It will be an exponentially larger number, right? So if I rearrange this equation, that goes microstates equals E raised to the SM, and I'm going to change this. That's going to be divided by R if this is in joules per mole per K, and that is in, right, I should really just say like or R, depending on the right units that we've used. So again, in rearranging that, you can see that as entropy increases, the number of microstates will exponentially increase. Okay, so that's all that I wanted to say about that. We'll do more calculations on this in our live lecture.